Very good evening to all of you. Myself Kiran MP. I'm working as assistant professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar, Karnataka. In today's session, I'm going to discuss. I'm going to give you a brief comparison about three asymptotic notations: big O, big omega, and big theta, which plays a very crucial role in the analysis of performance of various important algorithms. Of this, let me first have a look at big O notation. Um, Now we have seen various type of functions, right? Such as we used to identify those functions in mathematics, stating as constant or linear, quadratic, cubic, exponential. So each algorithm's performance is represented by the order of growth of some functions. Those functions may be linear, maybe exponential, or maybe logarithmic. So how we are going to compare two different algorithms which are solutions for the same problem type. Sometimes we say quicksort is better than bubble sort, right? Quicksort and bubble sort a solution for the same problem, that is sorting. But we are going to evaluate which one is better. So suppose first we need to analyze both quicksort and bubble sort. We need to represent its performance by the in the form of some function, and then we are going to compare that function with some other function. We are going to call that as big O of something, or big omega of something, or big theta of something. Got it? So now let me tell you. We have two functions. So let one function be identified as t of n. The second function will be identified as g of n. Suppose t of n's order is lower than or equal to the order of the second function, that is g of n, then we call t of n to be in big O of g of n. When we plot a graph for these two functions over time, okay, we can always see the graph for t of n will be lying below or equal to the graph g of n. So in this, let me say I said if the first function's order of growth order is lower than or equal to the order of second function, the first function we call to be in big O of the second function, right? So look at here some examples. So in the first function, n belongs to big O of n square. I have written there. N is, we know it's a linear, whereas the function which is at the right side is quadratic. So we know linear is always less than quadratic. So linear is always in big O of quadratic. Similarly, the second function, second example, 100n plus 5, which is linear, is again it's in big O of n square. Similarly, the third function. Now we will have a look at some functions which are not in big O of n. So if first function's growth rate is greater than the second function growth rate, then we can't say first function to be in big O of the second function. See, these are some examples. So in first example, LHS functions cubic, whereas RHS is quadratic. So cubic growth rate is greater than quadratic. So cubic can't be in big O of quadratic. Similarly. So now we will have a look at the second function, that is big omega. Big omega here, suppose the first function t of n's growth rate is greater than or equal to the growth rate of second function, that is g of n, then we call t of n to be in big O of t of n to be in big omega of g of n. If the first function say cubic, okay, second function quadratic. Cubic growth rate is greater than or equal to quadratic, right? So I can call cubic to be in big omega of quadratic. So these are some example. So I said, if I want to say function t of n to be in big omega of g of n, the growth rate of t of n should be greater than or equal to the growth rate of second function. And now we'll have a look at one more function, that is big theta. Big theta means suppose we are given a set of functions. If all these functions growth rate are one and the same, then we call all those functions mutually and big